In this video, we're going to be talking about how in projectile motion, an object is moving with a constant and accelerated motion all at the same time. So that's a pretty complicated concept because those types of motion are pretty opposite of each other, where constant velocity just maintains a certain velocity the entire time, and something that's an accelerated motion is changing the entire time. Now, the reason why a projectile exhibits both all lies in what happens with the forces. So, with a projectile, let's say it has a certain angled velocity of 20 meters per second. We'll say the number doesn't really matter that much right now, but we'll say 20 at maybe an angle of 30 degrees above the horizontal. Now, because it's tilted upwards, it has some vertical component, which we'll call Vy, and it has some horizontal component, which we'll call Vx. Now, as it's projected into the air, we only have one force acting on it, assuming that there's no air resistance. So if we take a look at it along both axes, we have an x-axis and a y-axis. As it's moving through the air, remember, velocity does not mean that there's a certain force acting on it. For example, if something is moving up, that doesn't mean it has a force being applied upwards, just like if something is moving to the right, it doesn't have a force being applied to the right. Now, once it gets tossed into the air, there's only a single force acting on it, which is Fg, the force of gravity. Okay, now the question is, well, how is it moving upwards and how is it moving to the right? And that's because initially it did have some kind of unbalanced force, like maybe someone kicked it or threw it, but that unbalanced force is gone. So that unbalanced force did provide some horizontal and vertical component upwards and to the right, but it's no longer there. So now when it's in free fall and it's moving on its path, it only has a force acting in the vertical direction. Therefore, there is a net force. And if there's a net force or an unbalanced force, that means it is accelerating. In the x direction, it does not have any forces acting in this direction. So because there are no forces acting in the horizontal direction, that means that there is 0 newtons of net force, or just none at all, which means that it is moving at a constant velocity, which means it's either not moving at all or just maintaining whatever velocity it had. Okay, so now let's go ahead and do an example problem so you can kind of see where we're going with this. Now, as the thing moves, it has some sort of Vx, and the Vx is the adjacent side of this 30-degree angle. So we can go ahead and say that 20 times the cosine of 30 degrees is our x component, and that would mean our x component is not 30, it is 17.32 meters per second. And then in the y component, because it's opposite of the 30-degree angle, we're going to take 20 times the sine of 30 degrees, and that's going to give us 10 meters per second. So as the projectile is moving, it has 17.32 meters per second of velocity carrying it sideways, which means that for every second it's in the air, it's going to scoot over 17.32 meters horizontally. So if you give it more hang time, it will keep on sliding you over 17.32 meters for every second it's in the air. Now on the y side, we have an initial velocity of 10 meters per second, but that's going to be changing every step of the way because of gravity. It's experiencing negative 9.8 meters per second squared. Now, this VI is going to depend, or is going to create the maximum height and the total hang time, because that displaces it vertically. So what we can do is, if we wanted to solve for something like a delta x, we could do a few different steps with that. So we can say that VI is 10, and then when it comes back to ground level, it's going to be moving the same exact velocity, but downwards, so that's negative 10. So we can go ahead and plug that into this formula right over here, and that's going to allow us to get our total time. So let's go ahead and do that. All right, so we got a time of 2.04 seconds, and time is not a vector, so you could place that into this column, and you can put it into this column over here, which is helpful to us because if we're solving for something like a range or a delta x, then we're going to use our constant velocity formula. Whoops. We're going to use our constant velocity formula right over here, and then solve for something like a delta x. So we know that the velocity is 17.32 equals delta x over t. And then we can take that 2.04 and cross it over here, which is basically multiplying both sides by 2.04. And then we get a delta x of 35.35 meters. All right, so to sum things up, as the projectile is moving along, remember, because there's no forces in the horizontal direction, this Vx is going to maintain that same 17.32 meters per second of velocity that entire time. For the vertical velocity, it starts off at 10, but it's going to progressively shrink to nothing at its peak. And then as it's coming back down, it's going to be moving in the same direction as the pull of gravity, and because they're working together, it's going to cause it to speed up, and that's why I made that vector a little bit longer. So as it's rising, it's going against the FG, so that vector is shrinking down into nothing eventually at the peak, and then as it's working with FG, that vertical velocity is going to get progressively larger in the negative direction. Now, every time you set up one of these problems, you want to be sure to separate them into an X and Y column because they're two different kinds of motion. So you're going to have to use different sets of formulas. In the horizontal side, you're only going to be using the V equals delta X over T. On the accelerated side, you can use your three acceleration formulas and always use that negative 9.8 to help you figure out whatever values you're looking for. So I hope that was helpful in helping you understand the concept of how the constant velocity and accelerated motion work with a projectile problem and how to set a problem up. Thank you for watching and listening.